Bad. The bad and the ugly. All right. Okay. So a recap a little bit. So what I'm presenting is a large-scale biomolecular simulations and what kind of calculations can be done, what are the limitations, what are some of the tricks that you can use to enhance sampling and to either enhance sampling for thermodynamics or to do it for kinetics. And so it's a continuation of the, this is an old West movie, it's actually from the 70s. It's called The Good, the Bad, and the Ugly. And was with Clint Eastwood, who I think was the good. The the guy in the middle is the bad. Look at his face, and the ugly is the Mexican. And one, the Clint Eastwood, who's the gringo, does something to the Mexican, and the Mexican from top of the hill says, "Gringo, hijo de puta." I don't know if everybody understood. Uh, and so it's a wonderful movie. So yesterday at the restaurant, they were whistling, which is the song that goes along with the movie. Huh? It was shot in Spain? Okay, that explains some of it. Yeah, actually, it's a fantastic movie. So the good, uh, Victor is going to like this, is proteins and peptides, systems that to some degree it behave reasonably well. And like he was saying, what is the difficulty, right? There is a entropy enthalpy compensation, there is a funnel, there is principle of minimal frustration, and then you're more interested in violations of that. And then comes the bad. The bad is nucleic acids. As far as I know, we have not identified a principle of minimal frustration. There is no minimal frustration in a nucleic acid. However, they fold and they have dynamics. So it's not that they don't have it, it's just that we haven't found it out. It's not as simple as a landscape that you can actually make a lattice model with more letters and you actually get rid of the roughness. The problem with nucleic acids is you have 4 letters, A, C, T, G. Yeah. And then the solvent, the context, and everything else might be dominant. And I will end up with the ugly, which is the protein, membrane proteins, or protein interacting with lipid bilayers, or even the lipid bilayers. So the bad, I showed that the last time. And of course, I'm not going to be working on this. This is the 16S fragment from a ribosome. These have been studied from the point of view of evolution by Wus is the pronounce. He passed away a few years back from Urbana-Champaign, and he studied the evolution based on sequence alignment and secondary structure analysis of the 16S RNA. And the interesting thing is that he found these regions in here that I am labeling in yellow are what is called tetraloops. So tetraloops are hyperstable, so they melt about 30 degrees C above the melting of other RNAs of the same size. They fold in microsecond time scales. And when you look at the evolution of these sequences, one tetraloop is replaced by another tetraloop. So you don't get a mutation that only one base is mutated. When you look at the conservation for different organisms, actually, you get the whole tetraloop replaced from one organism to another. So here we have, here I put the 3 general motif. So it's GNRA. So these two could be anything, but the first one is a G, the last one is an A. So any is N, and this means it's a purine. So GCAA is an example of a tetraloop. Another one is a UNCG, and again, this is anything. So UUCG is one of those, and CUUG is the other motif. So these are the 3 general motifs that are these hyperstable systems. So that makes it as a cool system that plays the role of the beta hairpins and the alpha helices that Victor started working at the kinetics, and there have been experiments on it. So I started being interested in RNA in part because it's a difficult problem and you want to see what are the difficulties, what is the problem. And this paper by Bevilacqua and Grubele came out in 2008, and they actually did a very detailed analysis of the folding kinetics of this, in this case, the GC UUCG. So notice that these two little bold, little lowercase letters is the stem. So essentially you're going to have a stem, a loop. The loop is the UUCG sequence, and then another GC that just base pairs with it. This segment is a little segment. If you look at the 30S ribosomal, you take a fragment of it, and this is bound in here is protein S15, but here is the RNA part of it. If you look at this little tip, that's what that is. And here is essentially extracting this out. So this is the system that Grubele and Bevilacqua studied. So Grubele, as was mentioned before, studies fast folding using temperature jumps and so on. This is what they did here. And then Bevilacqua is the expert on RNA, and in particular on these tetraloops. And this was a statement from their paper, and it says, even a fast-folding 8-mer RNA with an ideal tetraloop sequence has a rock energy landscape, ideal for testing analytical and computational models. So actually, I was working on a different sequence, so I switched and started working on this sequence to see if it's really a challenge or not. And here is the system. Here is a movie. The rules about when you make a presentation, when you believe your data and it's solid, you make it black and white with error bars. When you're a little bit flaky, you remove the error bars. When you're a little bit flakier, you make it in color. And when you don't know what the hell is going on, you make a movie. So that's a movie. And here, the scheme is blue base pairs with blue, red with red, and then this is supposed to be the the UG base pairs that actually it doesn't form. And this is from a simulation. This is about, what was it, half microsecond or so, 225 nanoseconds. Replica changed, as I mentioned before, because it's a way of enhancing sampling. And when you look at the structure, it's about 1.8 angstrom away from the folded state. You can declare victory, you did it, great, it's all wrong. You declare victory because you formed the stem. But the stem is not the relevant part of this protein, of this RNA, it's the loop. The loop is, the stem I should have chosen any other stem. It is the loop structure. So when I say the backbone 1.8 is because it's a loop. But when I look at the details of the loop, it's just not correct. I'll show you. I may have it later, the comparison, the detailed comparison between the two. Even worse, if you look at in this kind of calculations, you actually get an ensemble of the states at a given temperature that you're interested in, and actually you can follow the thermodynamics for the system. If you look at the most stable cluster, essentially the cluster that is the largest cluster that you get at lowest temperature, which is the temperature at which the system should be the most folded. If you look at the structure, this is what it should look like. This is from either the X-ray structure, and you can argue the X-ray structure is different because it has S15 protein on it and is part of a bigger compound. There are NMR structures on these tetraloops. So this is the structure. Notice the GC base pair, great. The GU base pair was not formed. And then the other two bases stack on top of the bases in here, and I don't have any of that. So essentially, everything here that is in yellow is incorrect. But when I look at the most stable state is this one. And honesty is very important. This was put in the paper, say this is the most stable state, and it's completely wrong. Because this state, you're supposed to have the GC two base pairs, and you're supposed to have the GU base pair, and then the two other bases stacking like this. The most stable state is this. There is absolutely no hydrogen bond between bases, 0. So notice blue instead of base pair, they're stacking like this. Red stacking like this, and then the 3 yellows are one. The 4 yellows are one on top of another. So it's a hydrophobic collapse. And so that's exactly part of the problem. And another part of the problem is that in the force field, the way it was done then, this base here could not do the transition from syn to anti. And to make the GU, you actually needed to have that transition. I'll study other sequences for which this is much more relevant, like a closing with a GA. So many things were wrong. Even though you can make a nice movie in color, you cannot publish the movie, but it looks like it folded. But we were not satisfied with that. So what's wrong? So what's wrong from 2008 until 2013? That's what we try to explore. How do we fix that? And what's wrong is the hydrophobic collapse. So if you just take the nucleosides, put them in water, and you measure what is the association constant, the association constant is 2. It's between 2 and 3. If you calculate the association constant with amber, it's 2,000. So you put it in solution, everything puts in together. If you look at the syn to anti transition in the force field, it cannot happen because it actually had a huge barrier and it couldn't happen. So that needed to be adjusted. And then if you also have this very strong association constant for the bases, when you look at the stacking, the equilibrium is also driven towards stacking. That's why everything likes to stack the way we got it. And so we actually studied this process, and we studied this process as a function of temperature because there is a entropy and enthalpy compensations or lack of compensation. And this is a very good way of measuring what's interaction of the solvent with the RNA. So this, interestingly, so this is the data that is needed, and it was all published when I was in elementary school. So the association constants was done by Sauce, 1963, Solly and Shellman, 1968. The ultrasonic absorption for the syn anti was studied by Schimmel, 71, and NMR in 1990. It's really new data here. And then this stacking as a function of temperature was studied in 1972. So the data was there. So we actually went after the data, and let me give you a little bit of what we did. So the reason we committed sacrilege, so we're going to be burned at the plaza, I'm going to be burned at the plaza, because I did something that for people doing simulations, you cannot do. I changed the van der Waals radius of the atoms. So if you look at the hard sphere in water, the hydrophobic effect gets stronger as the sphere gets larger. So if you have a sphere that is a little bit too large and you don't want to change the water model and the hydrophobic interaction is too strong, make the spheres a little bit smaller and you reduce the hydrophobic effect. So how we did it? We did it in a very smart and intelligent way. Yes? I'll tell you now. Yeah. So we did it in a very smart and intelligent way. We took sigma and actually an epsilon, and then we took sigma and we multiplied sigma by 0.99, 0.98, and at 0.95 you get association constant to be 2.6, 5%. Now, do you believe sigma is to 5%? No. if you actually look at the sigma parameter in the small crystal database, is about 10% smaller than the sigma parameters used in force fields. Because, and actually I presented this, and Levitt told me, of course, obvious. When we started doing simulations, we were doing calculations, we were doing energy minimization. When you have energy minimization, you don't have fluctuations, you don't have cavitation. So you needed to include a little bit larger van der Waals, such that when you created a protein structure, you get the minimum structure that is the crystal, but the crystal had thermal fluctuations. At the time, people didn't do cryo crystallography, they were actually doing at room temperature. So he increased the radius a little bit, and those radius, everybody copied without ever citing anybody, and that's what people have been using. So the sigmas just were a little bit too large. And then we also changed the epsilon, and the epsilon is changed by the same order of magnitude. And very simple. There is no theory behind. I know from hydrophobic effect that a larger van der Waals will give me a strong hydrophobic. That's why I went after the van der Waals. And then brute force. You have this system. Actually, we went 1.05, 1.04, just in case I was completely wrong. And then you see the trend going down. And at 0.95, you're done. So that took care of that. In here, it's just the dihedral angle of the chi value. And again, so you need a barrier. You can estimate, based on this data, you can estimate what the barrier should be and how often there should be transitions. It's in the nanoseconds time scale. So you actually look at simulations and you look at these transitions and you adjust the barriers. And then this is the hardest part. And I have the plots, but I don't want to go into all the details because there isn't as much time. But there is kinetic plots that is going to plot the rate of stacking and destacking of the nucleosides as a function of temperature, actually 1/temperature. And when you look at that 1/temperature, I should have shown that plot because it compares the different force fields. So if you look at the amber force field, the charm force field, and the force field that we got, the entropy for this process that you get from amber and charm is about a factor of half of the value that actually is measured. When we change using these parameters in here, we recalculated that it's about 80% of the value. So we don't have 100% for it. But the enthalpies are also reasonable. So that's the changes. Just change sigma and epsilon and actually tweak a little bit the interactions between water and the DNA bases. So instead of using the Lorentz-Berthelot combination rules, assume a small deviation from the Lorentz-Berthelot until you get the slope for the kinetic plots for the rates as a function of 1/temperature. And now I show you the movie. And again, let me see, what is the mouse? The mouse should be somewhere here. If I just click, nope. Come on. I lost the mouse. So this is a movie. This sequence is slightly different. So it's a GCGA. So this GA makes a G base pair that is actually a Hoogsteen base pair. It's not the typical Watson-Crick because there is no Watson-Crick for here. And then I'll show you later how it actually overlays with the structure. First, I need to get the mouse. Here it goes. So now you're going to see many different effects. For one, the system is a lot more extended. You don't have this quick collapse of the system. I'm going to show you another movie. In this one, the base pairs form right away. When we do really extensive calculations, we have done 100 microsecond simulations of this, you actually see that there's a lot of misfolding, and the system comes out of the misfolding. So now, first it made the GC base pairs, then the G was stuck, and the C was, the A was stuck, and then the G was flipping out, and it came in. So the GA is the actual right GA base pair, and then the other bases will stack. That's the actual structure. If I could, I'll wait for the end of the movie. At the end of the movie, I'll show the overlap between the two structures. There are fluctuations actually in a real molecular dynamics simulation, not a replica exchange. At the folding temperature, the system opens and closes, and it makes mismatches. But at the end of the movie, you're going to see an overlay between the NMR structure for this sequence and the one that we got, and there it is. That's 0.8 angstroms. So, and now it's not backbone, now it's all heavy atoms. Because before we cheated, we put backbone. That's what was 1.8, because the loop was incorrect. For the other one, the all atom was about 5 angstroms, which is really bad. And then you adjusted parameters. In no point we actually adjusted parameters to reproduce this structure. We were adjusting parameters for the nucleosides, and actually we adjusted only guanine. And then based on guanosine, we actually transferred the parameter for the others. So these are two other sequences. Actually, this is that one, so that's the 0.9 angstrom. The one with the GA base pair. This is the overlay of the two structures. If I can get the mouse to behave, haha. I'm completely blind on this side. I don't see anything. Yeah. Come on. Aha. So there is a view of the system when you actually rotate around, and you see the overlay is really good, and there are small fluctuations around it. And that's 0.8 angstrom. For the whole cluster, it's 1.3. And here is the UIUC, and that's 0.6 angstroms. Also, very good overlay between the actual NMR structure and the structure that we actually obtained. In the paper, I think I didn't include in here, we included a third one. Yes? Aha. It's too big. Yeah, yeah. Yeah. tRNA is 76 amino nucleosides. Yeah. Just the anticodon loop. We haven't done it. Yeah. 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 And it can be done in the context of the rest, so that will put some constraints and just search around. That could be done. Yeah. Thank you for the idea. Yeah. These calculations are expensive. In here is just the replica exchange. And what I'm showing you is that the structures were obtained. This was followed up by a grad student who just graduated last year. And to get equilibrium, he had to do 4 microseconds per replica. So it is about 3-4 months of CPU time on 512 processors, each calculation. No. Well, we use Anton for different things, because these are replica exchange for the thermodynamics that we look at the folding and unfolding as a function of temperature. We also look at folding and unfolding as a function of salt and counter and urea. That's my talk next week, so I'm not giving you that up yet. Yeah. A little bit of my talk next week. But that's so we have tried system of this size. We actually did one that has 2 more base pairs. So essentially it has 4 base pairs in the loop, and that one, it's overstabilized. So Chen, who's now a faculty at the SUNY Albany, he changed water models, and then using tip4p, he actually get the right equilibrium. But since he's doing that, I stay out. out of it. That's his 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 new job. Yeah. Yes. Oh yeah, it's called Chen Garcia force field, and everybody quotes it to harass us and say it's completely wrong because we changed van der Waals. You get cited either way. But no other force field have been able to fold at this level. Actually, there is a interesting paper by Cheatham that he compared this force field with the amber force field, and then the only force field for which the highest occupied cluster is the folded state is ours. The others is like much the sixth cluster or something like that. Yeah. Oh, it has to be only your problem. I see. Okay. Yes. Yes. For tRNA, I mean, the issue is, in part, we wanted to look at the small ribo switches or their small ribosime, but the small ribosime is 34, and we stay away from it. Actually, the student graduated, and he's a postdoc at Los Alamos, but with somebody else. So I cannot occupy him to do my problems. For proteins, the problem with the van der Waals radius, for proteins, the residues form neat liquids on their own in most instances. Tryptophan might be the only one that doesn't. But the OPLS, which is the one who did the most careful parameterization, essentially they studied neat liquids of benzene and neat liquids of a toluene. And each one of the side chains, they study the neat liquid, and they reproduce the density profiles and the temperature dependence profiles for those within around 300 degrees Kelvin or whatever. So those parameters were adjusted and fixed. And then for nucleic acids, if you look at the amber and the charm force field, they just took the van der Waals parameters from the OPLS for aromatics. But these groups are not aromatics. Actually, these groups are not hydrophobic in general. I mean, they are aromatics in the sense that they have these rings, but these rings are decorated with groups that are nitrogens, hydrogen bonds, carbonyls, and so on. So they are not, it's somewhere in the middle. But they don't form neat liquids. You can form crystals, but studying crystals, different story. Yeah. So if you look at this paper, let me tell you the punchline. We studied 3 sequences. We didn't study 2. The third one gave us 3.2 angstroms RMSD. And the third one, I don't have it here. I'll show you. I could pull it out and show it to you. But the third one is the sequence that has the UU here. And the NMR structure shows one of the U's going into what will be the minor groove and stacking in there. And we don't see that at all. We see them stacking like this, are stacking on top. And we mentioned that. I say this one, we messed up. There is something else that we don't have in the parameters. But let me finish my story before you ask the question. Then I was at the Trieste last year. I presented this, and there was a person who had done the NMR structure of that other structure the year before. And he says, your structure is the right one. The NMR structure from the 90s was wrong. Yeah. And our structure is 0.8 angstroms from her structure. And we published it the year before she did, so legit. We didn't know the answer. So at least in that sense. Now, in these problems, nothing is always so nice. These tetraloops do not need magnesium. That's why we choose them, because magnesium is a completely different, it's a different kind of worms. This is an American expression. Right? Imagine you have a can of worms. It looks pretty ugly. And So we didn't have magnesium. The NMR structure that Pardee did in the 90s, he had sodium chloride. He didn't have magnesium. The crystal structure, and I forgot her name, from Montreal, she had magnesium. So it could be the magnesium changed the structure. When I first saw the structure, I said, ha, misinterpretation of NMR data. And then Pardee had like 3 pages in a biochemistry paper on all the phosphate resonances between the base and the phosphorus in the groove. So that was well established. It was, I mean, I gave it to him, took my hat and say, your structure has to, I mean, it was not a sloppy job. It was a very careful job. In the 90s, to do NMR on a nucleic acid was a major undertaking. So you do it carefully. A person like Pardee will do it very carefully. So still there. Is it magnesium or not? Again, you know, hopefully at some point we have the energy to actually put magnesium into these systems and see what magnesium is going to do. You had a question? What reaction coordinate? I'm not doing kinetics or anything. Yeah. No, but I mean, comparing yeah. When you start with the open, I mean, what kind of barrier do you have? You calculate? You told me you have a method that can do all that trivially. I have 100 microseconds of simulation. Show me. Yeah. Yeah, yeah, I even have it here. Actually, I have it on my cell phone. Because it's all compressed. All I need is the RNA. This is 200, 300 atoms. Yeah, 300 atoms and 6,000 water molecules, right? And 1 molar potassium chloride. The reason for 1 molar and not 150 or whatever is that to include 150 and have enough ions, then I will have to do 20,000 water molecules. You know, challenges are somewhere else, not there. Yes? No, that's fine. There should be something for me, yeah. This, yes. Yes, yeah. Okay. That's always true for any simulations. All I can prove is that I have a steady state. And for replica exchange, what I do is I create an ensemble of all the replicas rather than looking at any given temperature, and I plot number folded, and I'm using RMSD within a given distance, number of replicas folded as a function of simulation time. And if I have, and this is for all of them. So if I have n replicas in here, actually you get this to behave like this. And this is about half microsecond. And then we go to 4 microseconds times 60 replicas. So it's 240 microseconds of simulation. So you can always claim it's not equilibrated. I can always find a parameter for which it's not equilibrated, right? And if I look at energies, it's equilibrated. If I look at variances of energies, it's okay. And if I look at the force moment of energy, it's completely unequilibrated, right? Because the asymmetry of the distributions and so on converge very slowly. So this is what we use. And this actually is not number of replicas, sorry. It goes like this. And I can show, the plots are in papers because this is what we use for equilibration. And then we use this. So we throw half microsecond. In some instances, we throw 1 microsecond. And we average over 1 to 3 microseconds. Any more questions? All right. So these are for the standard. If you look at most of the calculations that are done, Shitam is doing equivalent 1-2 microsecond calculations with replica exchange. So those results can be compared in terms of equilibration with ours. But most calculations are 500 nanoseconds, which we throw away. So here is the Anton calculation. So we actually, we had determined that the folding temperature was near 350 degrees Kelvin. So we decided to do Anton simulations at 350 degrees Kelvin because that's when things happen the fastest, right? That's when the system is going to fluctuate, and I want to see fluctuations. I don't want the system to be idle. And then we use this force field, and we simulated the GCAA. We can only do one. We actually produce 5 different simulations. We had the machine for 8 days, so that's all you can get. And there were 16, 18, 20, 20, and 25 microseconds. 16 and 18, why? Machine crashed, right? And then when the machine crashed, they reinstate your time. So would you throw away 18 microsecond simulations? I didn't. So we start again, and it crashed again, and the time is reinstated. Then we were running 20s, and then we had a little bit of time, and whatever is left over, you lose. So we ran until we exhausted all the time. So that's about 100, over 100 microsecond time. This I copied from Garcia. So she always shows the ribosome and zooms into it and whatever. So these little tips are part of the ribosome. And I show you from the secondary structure. So here is a movie is under the same. This is a 1.8 microsecond segment. Actually, this trajectory goes all the way to 25 microseconds. But I just want to show you, give you a sense for the kind of fluctuations that you actually have in the system when you're simulating. Now it's a straightforward MD. So if you want to study folding and unfolding pathways, this trajectory has about 8 events of folding and unfolding, and there are 5 of these trajectories. So we have 20-some events of folding and unfolding of the system. And, oh no. This is all theater, yeah. That's all we're simulating, yeah. And it's not in the context of the ribosome. So same scheme as before, we're gonna color, right, the things that are supposed to be paired. And you're gonna see that early on in the calculation, 2 of the 3 base pairs form. There it goes. It's done so quickly. Nope, it actually completely unfolds and tries again. And then it makes the wrong base pair. Now it has a blue-green base pair. It has a yellow-green base pair. It goes around. It's a really rough energy landscape. It's trying a million different things. Here you saw a base pair with one of the loop bases. And then, of course, I'm going to finish it when it forms all 3 base pairs. So we have plenty of trajectories on this. We have not analyzed the kinetics. Victor claims that he has this fabulous method that can map energy landscapes and pathways and everything, and he's going to show it to me Monday. I'm giving him the coordinates today. The method is written. It's a trivial thing, and let's see what Victor shows us Monday. No vision Sunday. Yeah. Okay. So that's for nucleic acids. We have done some other calculations on nucleic acids, but I just want to give you a taste for the different systems, the different challenges. For nucleic acids, the force field was a challenge. For membranes, the force field is a challenge, but nobody has solved it. And we haven't even tried too much to solve it. There is a force field that is called Charm 36, seems to do the best. And that's what we're using for most of the calculations. In this, we use the GROMACS force field for lipids. So the ugly. So why do we call it the ugly? I mean, membrane proteins are really, really relevant. And here is the problem. So a real membrane protein has probably 600 different types of lipids. And these lipids, some of them are in very minute concentrations, but when you say, oh, it's a minute concentration, that concentration might be higher than the concentrations of proteins on the surface. So it's not irrelevant, it's relevant. And then, so there are probably about 4 or 5 lipids that have been parameterized, and the results compare with experiments. From some 600, you have to go to 4 or 5. And then in those 4 or 5, you're going to look at the ones that are neutral or sweeter ionic. That's POPC or DOPC. Then there is the one that are negatively charged. Those are PS and PG head groups. And then there is the sterols that are cholesterol. Cholesterol is the only one that probably is reasonably well parameterized. And this is the structure of a membrane. So when you want to look at a function, not now just folding, actually folding in the membrane is out of the question. From the simulation point of view, even from the experimental point of view, it's very challenging. There might be 2 or 3 people who are actually doing it. But here is how it looks. So you have a really crowded environment, a membrane that can adopt all kinds of shapes. There are claims that can form microdomains and so on. And in this view, still pretty. Let's forget about that. In this view, it's ugly. You know, that's what I call it, the ugly. So these are calculations by Maring's group. This is using Martini. It's a coarse-grained model. I believe this has 65 different lipids, and it's a 20,000 lipids in the simulation, something like that. It's a really, really big system, but using this coarse-grained model, it can actually be done. And the different colors represent different ingredients in the lipid. And here you cannot even say it's a bilayer, and here is everything. So it's a really heterogeneous. Even worse, let me skip this, come back to it later. Even worse is the relaxation times. So the lipid bilayer, the lipids in the lipid bilayer relax very slowly. So if you look at the diffusion coefficient of a lipid on the bilayer, you get about 1 nanometer square of area covered in a microsecond. So if you simulate this system and you simulate for 100 nanoseconds, I pay a beer to anyone who can tell me the difference between one system and the other. Nothing changes. Right? You're going to get 2 lipids may exchange positions. That's it, in 100 nanoseconds. Most of the simulations are here when you look at the literature. So essentially, the lipid is there as a medium that is at whatever configuration you put at the beginning. If you put only a single lipid, POPC or DOPC, you're done, because they're all the same, and you don't need to mix. As soon as you put a lipid and cholesterol, now you need to mix. Otherwise, all you have is your initial condition. And it's not that you have good initial conditions for what the lipid should be, because you don't know how the lipid should be mixed. So here is a big challenge. And then, now I'm going backwards. And then these are systems that, this is a system we actually simulated. This is a, it's not, This is a GPCR bound to the G protein. This is a 1.2 microsecond simulations. So that scale up to 1,024 processors on a blue gene that we actually grab for a few months. And what you see here is all you see. It just doesn't. So essentially, when you look at a membrane protein and a membrane protein complex in the simulation, you see very much what we used to see in the simulations in the early 1980s. That's it. These things fluctuated a little bit. And whatever is supposed to happen here, velocity and so on, hard to see. There are simulations of hundreds of microseconds that, without the G protein, that people have seen a little bit of the allosteric change. They can see a ligand binding and so on. And these are calculations done with Anton on much smaller systems. When you put the G protein and you reduce everything, this is a 400,000 atoms system. So 400,000 atoms, and it takes a microsecond for a lipid to flip, to exchange from another. It's a difficult problem. So that's why it's the ugly. So what can be done? This is from yesterday, and here were same examples that Victor used to some degree. This is the Lapidus. So their processes are in the 10 nanoseconds, in the 100 and the microseconds, and so on. And when you put lipids, the microseconds time scale is for the solvent to relax. So when you do a system in water, water rotates in 10 picoseconds. Here a lipid is going to exchange in a microsecond. So before, for folding, we use a replica exchange, and then great. So let's use replica exchange and see what the system does. You cannot do replica exchange because the systems are too large. I just show you that a small lipid bilayer system may have 50,000 atoms. A system that is kind of relevant is going to have 400,000 atoms. So replica exchange doesn't work for the following reason. The number of replicas that you're going to need scales with the square root of the total number of degrees of freedom in your system. So the average energy at one temperature versus another temperature scales with the number of degrees of freedom times kT. The fluctuations in energy, proportional, this is the variance, the width of the distribution is proportional to the square root of the number of degrees of freedom times kT. And then the energy difference between the energy at one temperature and the other at another temperature to do the replica exchange is going to be proportional to this number in here. So the problem is when you have a very large system, typically the systems I show you, the difference in temperature between one replica and another is about 5 degrees Kelvin. And then you need 60 replicas to span 300 degrees or something of that order. For a membrane system, the system is going to be 10 times bigger, so the temperature is going to be 3 times smaller. That's 1 degree jumps. First of all, temperature coupling algorithms and the fluctuations in temperature that you actually get from your heat coupling algorithms are larger than that. So you're never going to be able to actually adjust temperature at that fine scale of below 1 degree Kelvin. And then you're going to need 300 replicas of a system that requires 1024 processor to get a microsecond in a few months. So out of business. It's you just cannot use replica exchange. So what can you use? And here is the reason for this is to actually show you a method that we stole from somebody else and just apply it to lipid bilayers. So in 2005, Bruce Byrne postulated a method that is called the solute tempering. So it's a method that actually failed completely for do protein folding. And the reasons I think Victor showed today is imagine you want to do protein folding, and what you're going to do is that you're going to temper the protein, and you're going to keep the solvent at room temperature. So the compensation at the barrier height for the entropy, you're not going to get it because the solvent is frozen, is slow. So you cannot decouple the solvent from the protein. And in here, you don't want to couple the solvent and leave the protein because the solvent is the large part of the system. That's where the system becomes slow. So what we did is that we actually applied this method, and this method is very much a variation on something called Hamiltonian replica exchange. So I can do replica exchange that instead of changing temperatures, I change the Hamiltonian. So I can do the sampling in one Hamiltonian and then do exchange with another Hamiltonian that is similar, but it's a perturbation on that one. And essentially, I'm sampling the coupling of this extra Hamiltonian, this perturbation of my general system. But the trick here is that you separate your system, the total Hamiltonian, into solute-solute, so how the solute interacts with itself, solute solvent, in this case, solute water, in the general case, and then water. And this has the most degrees of freedom because the solvent is about 95%, 90 to 95% of your system always. So this you don't want to temper. You actually want to temper this. And for the lipid, I'll show you what we tempered and what works and what doesn't work. And the trick is the following. So you take the Hamiltonian and you're going to scale the different terms. This term you're going to scale by the temperature at which you're simulating for the replica exchange divided by the temperature that you care. So this is going to go from 300 degrees Kelvin to 350 or 400 or 600 or whatever you want to do, and this is going to stay fixed at room temperature. So this is the one that you fix. And then you scale this. So essentially you make this term either stronger or weaker depending on the, so if this one is 300 degrees Kelvin and this one is 600 degrees Kelvin, so essentially this is 1/2, this term in here. So you weaken the solvent-solvent interactions by 1/2, and essentially you lower all the energetics and the thermal fluctuations will be larger. And then this one you don't temper at all. So you always simulate this at the temperature that you're doing simulation. And this one you have to resolve how you're going to do it. And actually you can do it almost many different ways, but it's very convenient to do it this way because if I put the square root of the temperature at which I'm simulating divided by the temperature that I care about, when I multiply by beta 0, when I simulate that m equal to beta 0, this term is 1, so I get the intact Hamiltonian, and that's the configuration, that the ensemble that I really care about. And there is an extra term in here. But when I multiply this by beta 0, which is the temperature at which I want to sample, and I multiply it by HM, I get essentially beta M HSS, because the beta 0 is going to cancel. I get this one. And then this one is going to be beta 0 HWW, which is the exact value that I want. And then this one is going to have beta 0, beta M square root of it. And when beta M is a beta 0, you get beta 0 out, which is the system that you want. And then if you look at GROMACS or whatever, the Hamiltonian replica exchange is implemented there. So all you do is that you take your Hamiltonian, you multiply by this coupling constant, the different terms, and you simulate with that. And then you exchange energies between them. So this is the system we're doing. So we take a lipid DPPC, 144, so essentially 77 lipids on each one of the 2 layers. We put cholesterols into it, and to do that we created a lattice of 12 by 12, and we inserted, so it's about 40% cholesterol of the total number of lipids. So we put the cholesterols at random on the top layer, and we put the cholesterols at random on the bottom layer. And then we're going to do MD, and we're going to do the solvent tempering, and we're going to compare the equilibration of this system. What does it mean, equilibration? That the radial distribution functions of the lipid cholesterols are the same on the top layer and the bottom layer. I took out the crucial slide. The crucial slide is that when we do this tempering scheme, I need 6 replicas because the number of degrees of freedom that I tempered is so small that to go from 300 to 600 degrees Kelvin, I can do it in 50 degree steps because I still have overlap of the energies, because I have a couple hundred atoms, couple hundred, less than 1,000 degrees of freedom for the system. Actually, the way we did it is, well, that I know I have in here. So the trick is, what do we temper? Tempering the water, out of the question. So essentially, it doesn't solve the problem because then it will be as bad as replica exchange. You may need hundreds of replicas to actually sample. So possibilities, you take the DPPC plus cholesterol, so you take all the lipids and leave the water at the temperature that it was. You take the DPPC and you temper only the DPPC and don't temper the cholesterol, or you temper the cholesterol and don't temper the DPPC. And I'm going to show you very quickly this. Well, yeah, this doesn't work because cholesterol is a very small molecule that has very little interactions with the esterol. With the there is an oxygen that is polar that interacts with the head groups and the solvent, and as soon as you temper, it actually goes into the center of the bilayer and stays there, because the center of the bilayer is very hydrophobic and it has a lot of space, so you can actually open cavities and put a hydrophobic group in there without much penalty. So you drive the system towards a different phase. So it's a kind of a phase transition. The system goes into a different phase that is going to take forever to get out of it, so you don't want to deal with those phase transitions. Imagine that you do replica exchange and then you get water vapor. And then when you cool, you have to nucleate and condense the water. It's not going to work. That process is slower probably than folding, so you don't want to do that. So I'm going to show you the doing it this way. Actually, this is the way that works the best. So don't temper the cholesterol. In here, if we temper the cholesterol, we had the same problem that the cholesterol is going to go into that different phase. So this is the way that we actually did it. And this is the configure. Well, this is why you don't want to temper the cholesterols, because they go into the middle of the bilayer. So so here are the advantages of this. So I told you you needed about a microsecond to have a nanometer square of sampling. Here is the diffusion coefficient that I get by just looking at the displacement of a lipid relative to what it was before, and as a function of time. Time is in here. It's funny because I'm changing temperatures, so it's not. Out of all the replicas that I'm doing, the one at beta 0 is real. All the others are completely fictitious, and I'm talking about simulations where everything is fictitious. So if you calculate this coefficient, diffusion coefficient, this is the diffusion coefficients that you actually get for the solvent tempering for each one of the components. And interestingly, we did not temper the cholesterol and still diffuses faster, because the neighbors are diffusing faster, so the cholesterol can actually have a much faster diffusion, and then the lipids, of course, they diffuse faster. And this is the relative cholesterol diffusion, one cholesterol related to another, cholesterol, the DPPC, and the DPPC diffusion. So it's an order of magnitude larger than this one, and it costs 6 times, right? So the time scale is an order of factor, an order of magnitude larger, so it gives you faster equilibration, or at least faster sampling, faster mixing of the lipids. But you don't gain everything, because out of the 6 replicas, 1 is good, the other 5 are not good. They don't represent any realistic thermodynamic system. And here's the radial distribution functions. So, so this is the solvent tempering, and notice that within 50 to 60 nanoseconds, the radial distribution of the top layer and the radial distribution of the bottom layer that are completely independent, they converge. For the MD, we needed about 240 nanoseconds to get convergence at close distance and no convergence at higher distance. So it's much faster than the MD, and then it allows you to at least equilibrate a system before you engage into a simulation. So if you put a membrane protein like I have there, the GPCR is going to have preference for one lipid versus another because the surface is not just a hard sphere. It has some different interactions. And if you don't know what that distribution is, which is the case, actually crystal structures do not have lipids. So you don't know where the lipids are, or at least they don't have a bilayer. So you have to figure out what will be the preference of the protein for the lipids. You can actually run this with the solute tempering, equilibrate the lipids within the context of the protein. You can even keep the protein at room temperature, don't temper the protein, and just equilibrate the lipids. So we are actually working on that for studying all kind of membrane systems, including GPCR, RAS, GPCR, RAS, and RAS binding to other effectors. Ooh, time is over. So pros and cons, it accelerates sampling. The cons is that everything that is not room temperature goes to the trash. It's useless. So you cannot calculate thermodynamics because half the system is hot, the other half of the system is cold. That's not equilibrium. So it's useless in that sense. And then what's next? And I mentioned a little bit of the challenges. So imagine, typically you see these kind of networks shown, and imagine you want to study little bit of the events at which these couplings actually exist, and we're interested in particular at this protein in here, RAS. So RAS binds, given that RAS is in the GTP bound state, it's active. When it's active, it binds RAF, and then the RAS is attached to the membrane. The RAF is not attached to the membrane, and if you put the GDP bound, RAS doesn't bind. And imagine you want to understand different effects of this. What are the different effects? Crowding. So you have a surface that should mimic what a cell membrane looks like. So if you want to, you have this protein and this protein, and this protein needs to diffuse, say, on the surface to bind to this protein. It cannot just diffuse like this because it has to go around obstacles. So we can actually put obstacles very fictitious way and explore what are the roles of fluidity in the membrane, essentially things that are slow versus things that are fast, obstacles in the membrane, effects of binding versus unbinding, for example, of RAF. And this is a big challenge. So this is something that you can actually simulate at the multi-scale because you need to simulate it for seconds. And you cannot do atomistic for seconds. So you actually have to identify events that occurred in the microseconds to tens of microseconds time steps, and that's a time step in your calculation. So this is the future. Will it ever get done? I hope we get this done and stop there. The rest of the thing, when you look at the systems biology modeling, they don't put any diffusion, they don't put any spatial resolution in general. Zen Schulten is actually doing a bacterial system where she includes diffusion and so on. But it always assumes that this is a beaker where all the solutions are well mixed. And they're not well mixed, they're actually localized at the membrane bilayer in specific places. So like RAS is going to be nearby these kinases because actually these kinases are the ones that have the proteins that activate RAS. And that binding is important for the activation, or at least one event drives the other, so they actually have to be, if they're nearby, it's more likely to occur than if they're not nearby. So those effects are important. So this is, where do we go next? Why are we thinking, where do we go next? Like Victor said, folding is done, right? Yeah. So we want to stay entertained with a problem we know we're not going to solve. Yeah. Thank you.